Physics begins with understanding motion. Motion is everywhere around us, from cars driving down the street to planets orbiting the sun. To describe motion precisely, we need to understand several key concepts. Average velocity tells us how fast an object moves over a period of time. It's calculated by dividing the total displacement by the total time taken. Constant velocity means an object moves at the same speed in the same direction. The velocity doesn't change over time, creating a straight line on a position-time graph. Instantaneous velocity is the velocity at a specific moment in time. Unlike average velocity, it tells us exactly how fast an object is moving at one particular instant. Acceleration occurs when velocity changes over time. It can be speeding up, slowing down, or changing direction. Acceleration is measured in meters per second squared. Free fall is a special case of motion where objects fall under gravity alone. Near Earth's surface, all objects fall with the same acceleration of 9.8 meters per second squared, regardless of their mass. Now we move to Newton's laws of motion, which form the foundation of classical mechanics. These three laws explain how forces affect the motion of objects. Before we explore the laws, we must understand what a force is. A force is a push or pull that can change an object's motion. Forces have both magnitude and direction, making them vector quantities. Newton's first law, also known as the law of inertia, states that an object at rest stays at rest and an object in motion stays in motion, unless acted upon by an unbalanced force. Newton's second law gives us the famous equation F equals ma. The net force on an object equals its mass times its acceleration. This law tells us exactly how forces change motion. Newton's third law states that for every action, there is an equal and opposite reaction. When you push on something, it pushes back on you with the same force in the opposite direction. Physical models are simplified representations that help us understand complex phenomena. Newton's laws are models that work extremely well for everyday objects, but they have limitations at very high speeds or very small scales. We now expand our physics knowledge to explore energy and momentum, fundamental concepts that govern motion and interactions in our universe. Energy begins with the concept of work. Work is done when a force acts on an object and causes displacement. The formula shows work equals force times displacement times the cosine of the angle between them. Kinetic energy is the energy of motion. Any moving object possesses kinetic energy equal to 1/2 times mass times velocity squared. The faster an object moves, the more kinetic energy it has. Potential energy is stored energy due to position. Gravitational potential energy equals mass times gravitational acceleration times height. The higher an object is positioned, the more potential energy it possesses. The law of conservation of energy states that total mechanical energy remains constant in the absence of friction. Energy transforms between kinetic and potential forms, but the total amount stays the same. Momentum is the product of mass and velocity. It describes the quantity of motion an object possesses. Momentum is a vector quantity, meaning it has both magnitude and direction. The law of conservation of momentum states that in a closed system, total momentum before collision equals total momentum after collision. This principle helps us analyze collisions and interactions. Physics extends far beyond mechanics and energy. Thermodynamics studies heat and temperature relationships. Electricity explores charges, currents, and circuits. Nuclear physics examines atomic nuclei and radioactivity. Modern physics introduces relativity and quantum mechanics, revolutionizing our understanding of space, time, and matter. These fundamental concepts of energy, momentum, and advanced physics topics form the comprehensive foundation needed to understand the physical world around us, from everyday motion to the most exotic phenomena in the universe.